linear inequalities. So with linear inequalities, we will see some of the matrix stuff show up again, but in the meantime, we're going to start off by just talking about inequalities. Now, you're probably all familiar with inequalities. Greater than or equal to, less than or equal to. Something that may not be as familiar is some key phrases that correspond to these inequality symbols. Greater than refers to, if you see the word over, so this is over that, then what's synonymous to that is thing A is greater than that other thing. So we can kind of compare this, say, example 1, part 1, the price is over 7,800. So the price is over 7,800. So we could keep going. The height is not less than. Well, if it's not less than, what does that mean? If it's not less than, then it has to be, well, the opposite of less than is greater than or equal to. That's the complete opposite of less than. So not less than means greater than or equal to 1,400 feet. Enrollment in finite math, which they say is X, plus enrollment in calculus, which they represent as Y, is less than 700. So that's how we would read and translate some of these. And then the last one's a little bit tricky. I figured I would just tell you all this one because this is more of a my math lab nitpick than anything else. If you try to read this directly, the savings X, so if you tried to solve this directly, at least, if you scroll up, at least corresponds to greater than or equal to 2,400, or 1,000 rather, under the revenues, but this is not correct. So instead, this one's a little tricky. Really what it's saying is that the savings are under the revenues. So the revenues, underneath the revenues are the savings, and their difference is at least 2,400. Again, kind of tricky. Figured I would just give you all this one. But my math lab will not accept this answer for some reason. They want you to solve for X. Not too sure why, but figured I would show you all how to do that. So solving for X, of course, you would add X on both sides. And so you get that Y is greater than or equal to 2,400 or 24,000 plus X. But they still won't accept this answer. They want X completely by itself. Again, just a random formatting thing. So you would have to subtract 24,000 on both sides. Y minus 24,000 is greater than or equal to X. And that's the answer they will accept. Yes?
Would you do that with 3 too?
What's that?
Would you do that with 3 as well?
Surprisingly, no. It's just they decide right here, for this problem in particular, you got to solve for X.
That's the only one that's like
That's the only one that's like that. So I just wanted to kind of give you all the answer. Again, that's just an annoying my math lab thing I noticed. But yeah, for part 3, they're perfectly fine with that form. So again, that's just a my math lab thing. Okay. Let's move on to example 2 here. So example 2, so now that we've established this way of converting, I guess, verbiage to inequalities, now that we have inequalities, we want to determine if an ordered pair solves a given inequality or equation. And we will be doing this actually throughout this section, applying this process here. So to figure out if an inequality is satisfied by an ordered pair, we have to plug in the ordered pair, which always gives us an x and a y. So the inequality is all the way over here. The y is 17 minus 3x, and x is 9. And basically, do we get a true statement from this, or do we get a false statement? Well, let's work this out. I believe that this is 7. 2 times 17 is 34. 9 and 2, 34. Yeah, that seems about right. So is 7 greater than or equal to 2? Of course it is. We get a true statement. And since we get a true statement, then this implies that the point is a solution. To the inequality. Point is a solution to the inequality. So what about, so that's the criteria for inequalities, and we'll see this come up again. What about for equations? What about the point 7, 1, if that's a solution to this equation, because there's no more inequality symbol, it's just an equal to sign. So it's an equation. It's the same idea though. We plug in x, we plug in y, we see and ask ourselves, does this yield a true statement? 2 times 7 is 14, plus 3 is 17. Is 17 equal to 12? Of course not. So we get a false statement. So we say the point is not a solution. To the, I mean, technically it's an equation. Last one was an inequality, so I said the word inequality. This is an equation, because there's an equal to sign. Does anyone have any questions before we move on? If not, let's move on to graphing inequalities. So we've graphed linear equalities. In fact, we did that at the beginning of this unit in the systems section. But now we're going to add another component to it. Not only are we graphing a linear equation, but a linear inequality as well. So that means that there will be some additional aspects to this process. Now, in order to do this, this breaks down into 3 things that we have to do. So here's the inequality. The first thing we have to do is graph the equality, the underlying equality. Which just simply means take out the inequality symbol and put an equal to sign there. You would graph it as if it were a standard problem from the very beginning of this unit. Now, what we did before was we found the x and the y intercepts by plugging in 0 for x, plugging in 0 for y, but they already gave us mx plus b form. We could figure out the line a lot more easily because they told us that the slope is 1 and that the y-intercept is 5. So they already gave us that. There's no point in having to find the x and the y-intercept. We already have all the information we need right here. The y-intercept is 5, which tells you a definitive point on the graph. And since the slope is 1, you would go up 1 and over 1. Up 1 and over 1. because the slope is 1. So this is very similar to what we did before. However, I'm not going to draw a line just yet because there's a second criteria here. The line that we draw will either be a solid line or a dotted line. So how do we know the difference? This one's actually the easiest one to determine. It actually says it at the very beginning here. The line will be solid if you have an equal to sign in your inequality. The line will be dotted if you don't. That's simply it. In our inequality, we don't have an equal to sign. So guess what we pick? Dotted. This is dotted because inequality symbol does not contain an equal to sign. That's it. That's all there is to this one. All we have is greater than, not greater than or equal to. So when we draw this line, we're going to be drawing it really as a dotted line, not as a solid line. And so you will have this ability to do this in my math lab. It will, whenever you select the line, it will also give you an option of putting a solid line or a dashed or dotted line. So that will look something like this. This is a dashed line on purpose. It's not a solid line. So that's 2 of the 3 steps for this inequality process. So the third step is something called shading. Now with inequalities, it's not good enough to say that a line represents the graph. Inequalities also introduce a whole entire region. So I think we can all agree that this graph has been split up into 2 regions. The region above the line and this whole region below the line. We have to determine which one of those 2 regions do we shade. Do we shade the top one or the bottom one? So the question is, how do we do that? Normally, the most default thing I like to do is I like to use the point 0, 0, which it's the easiest one to find. It's right here in the center of the graph. So find 0, 0, and ask yourself, does 0, 0 satisfy the given inequality? And this is exactly what we did in the previous 2 examples. Does 0, 0, the point 0, 0, does that satisfy the given inequality? So the given inequality, I'll just remind everybody, is y is greater than x plus 5. That was given at the very beginning of the problem. We're going to plug in 0 for x and 0 for y. So I plugged in 0 for x, 0 for y. So 0 is greater than 5. Did we get a true statement from this or a false statement? We got a false statement. 0 is not greater than 5. So what does this tell us? So that's the question now. This means we do not shade on the same side that contains the origin or the point 0, 0. That's what this tells us. So we will be shading the region not containing the point 0, 0. So which region is that? Well, this is the region not not containing the point 0, 0. We shade that whole region. Now, how you do this in my math lab, so this is after you plotted your line and you told my math lab whether to make the line solid or dotted. There's a paint bucket tool. And once you click on that, after you draw your line, with your cursor, you click on any particular region of the graph and it will highlight that whole region for you. In fact, the paint bucket tool, I'm terrible at drawing, but it looks more like a deformed bird than anything. But yeah, that's kind of the idea, though. There's a paint bucket tool, and as long as you click anywhere on the right side or on the correct side of the line, it will shade that entire region for you, and it will look very similar to what I have here. As you all know, math people cannot draw. It's normally the commonality there. But does anyone have any questions before we move on to the next example? So we'll look at this a few times. In fact, this is actually something we will see because really we only have two sections left, this section and the next one. And we'll be doing this process for the remainder of this class, for this section and the next one. So let's look at the next one and see what commonalities we can make between the two, what differences this might yield. So they give us a new inequality, if anything, and same premise. We're going to plot the line. We're going to either keep the line solid or dotted, which you might already see which one's which, and then we're going to figure out which region to shade. So the first step is to graph x is equal to 3. I took out the inequality and I'll put an equal to sign. We are graphing the underlying equality here. So that one's kind of weird. How do you graph x is equal to 3? Means you have to kind of remember, what does that refer to? Well, there's no y value, which means there's not going to be a slope. So there's no slope here because there's not a y. When there's no slope, that means the slope's undefined. So in other words, this is a vertical line. It's a vertical line here, whenever you have x is equal to a number. Another way you could think about this, since that's the x-axis, here's 3 on the x-axis, and you're not allowed to leave that part of the x-axis, because if you do, then you would have x is equal to 7 or something. But it doesn't say x is equal to 7. It just says x is equal to 3. So this only allows you to go up and down, which that's another indication. That's something I tell my college algebra students when I teach that class. But we have, all you have to do in my math lab is draw any 2 points that will give you a vertical line at x is equal to 3. And so I just picked 2 points at random. This is definitely x is equal to 3. So you have to make sure the vertical line is there. You can't just draw a vertical line anywhere. From here, so there's nothing really to do there. There's no y-intercept defined because there's no y. And I guess that's another indication that you couldn't have a horizontal line because it cannot cross the y-axis. So there's nothing really to do there. It's just a vertical line. Part 2, we ask if this is dotted or solid. And since we have an equal to part in our inequality, so we have an equal to, then we pick solid. We have an equal to in the inequality. Which means, well, we don't have to do a dotted line here. We can just draw one continuous solid line. something like that. And then the third thing we have to look for is shading. Which side do we shade on? Because there's two regions here. There's the region to the left of the line, there's a region to the right. And we ask ourselves, which side do we shade? And what I like to do, again, is find the point 0, 0, which is right there. The 0, 0 satisfy the inequality. So that's what we're going to look for here. The inequality is x is less than or equal to 3. We plug in 0 for x and 0 for y. Well, there's no 0 for y, so there's not really much we can do. But we can plug in 0 for x, and we get a true statement, because 0 is less than or equal to 3. This is true. So what this tells us, since we have a true statement, we shade the region containing the point we just tested, 0, 0, which means we shade the left side, because the left side is where that point's at. Again, if you want to make fun of my drawing, I'll try to do a little bit better. I think it's worse, but that's okay. But you put the paint bucket tool anywhere on that side and it will highlight that entire region for you. You just play around with it for a bit and probably figure it out after a few seconds. But that's how we graph that inequality. Does anyone have any questions before we look at the next one? If not, let's go ahead and proceed to example 6 here. So now they give us the inequality 8x is greater than or equal to negative 7y. If anything, I know the line's going to be solid. That's one indication you can immediately make no matter what. So let's start off with graphing the equality. 8x is equal to negative 7y. Now, this is not in mx plus b form, so we don't get the slope and the y-intercept for free. This isn't in any other special form. So we could go ahead and find the intercepts. We can go ahead and find the x and the y-intercepts because they didn't give us this in a nice form. The problem here is if you find the intercepts, I'll just think ahead, you're going to find 0, 0 for both intercepts. So instead, I'm going to write this. If we divide negative 7 on both sides, we already have slope-intercept form. All you have to do is divide both sides by negative 7. And that's the transition I did. And now we have slope-intercept form. Because if you try to find the x-intercept and the y-intercept, you won't get two distinguished points, which means that won't help you. So we have to do this. So the slope is negative 8 over 7. The y-intercept is actually 0. There's no plus anything. So it's 0 by default. So the plus 0, since our y-intercept is 0, that gives us a definitive point. And the next point we find the slope tells us we go 8 down, 7 to the right. Or we rise negative 8, run 7, if you remember that from high school. We go down 8 over 7. We get the second point all the way over here. You have to go down 8 and to the right 7. That's how we interpret the slope. And from here, it's solid or dotted. This one should be the easiest one. It's solid because the inequality symbol has an equal to sign. So I am going to draw a solid line here right fast. Now we need to figure out which region to shade. Well, we can't pick the point 0, 0. Because 0, 0, well, here's one region, here's another region. The point 0, 0 is, the line splits right between it. So 0, 0 is not on any region. We can't really pick it. Because if 0, 0 satisfies everything, then what region do we shade? We don't know. Instead, I'm going to pick another point. I'm going to pick the point 1, 1. It doesn't matter which point you pick. Normally 0, 0 is the easiest one. So we're trying to determine, do we shade on the same side as 1, 1? So is 8 greater than or equal to -7? That is true. So shade on the same side as 1, 1. 1, 1 is over here. Let's give this one more attempt. So that's what we would conclude with for this problem. So we're going to be working backwards here. Instead of us be given an inequality and graph it on an XY plane, we're given the graph and we need to figure out what the corresponding inequality is. So here, well, one thing we can notice, so we need to figure out the inequality. So we're working backwards a little bit. We need to figure out if anything, all right, this is a horizontal line. And since we are given the line already, you can hopefully see that it's a dotted line right here. Hopefully that's evident to make out here. We could figure out the slope and the y-intercept and just build the line the easy way. So the slope of this, the slope is 0. That's always true for a horizontal line. Slope is rise over run. It doesn't rise at all. It doesn't go up or down at all. So that would be 0. And then run, you can think about that default as 1. So 0 over 1, slope is 0. And so the y-intercept, well, the y-axis is the axis going up and down. Where does it intersect the y-axis at? Looks like at -2. So if anything, this tells us the underlying equation that's going on. That's y is equal to 0x minus 2. You know, mx plus b. But the 0 cancels out the x. So really, we just have y is -2. So this isn't the inequality. This is the underlying equality. So we have everything right up to the inequality symbol. That's what we need to figure out now. So the question is, well, out of the 4 inequality symbols, is there any way we can narrow it down to, well, I guess eliminate any of these options? I'd say we can eliminate 2 of these options really quickly. The line here is dotted. Since the line is dotted, we have either y is greater than -2 or y is less than -2. Since we have a dotted line, as we talked about before, a dotted line corresponds to an inequality that does not have an equal to component. And so we can see here, since this line is dotted, that means there's no equal to in our inequality. So it has to be one of these 2 inequalities. And so really one way you can look at this might be more so intuitive. Is the shaded region above the line or below the line? Another way we can do this is to test 0, 0 on one of these inequalities. So I'll pick this one. So we're considering, is this the correct inequality? The correct inequality. We're going to test 0, 0. Remember, that's the point right here in the center. If we get a true statement, we should shade on that side. If we get a false statement, we should not shade on that side. What this tells us x is 0, y is 0. There's no x, so we can just ignore that. So y is 0. So we get a true statement from this, which tells you that you would need to shade on the same side as 0, 0, which would tell you you would have to shade up here. But our graph doesn't have that. Our graph shades on the other side. So what we just chose cannot be the correct inequality. And instead, it has to be the other one. More intuitively, this makes sense because y is less than -2, less than being it's beneath -2. So that could be some other indication that you can use to help select the correct inequality. So y is less than -2 is the final inequality that corresponds to this graph here. So that is the final answer. So does anyone have any questions before we move on to example 8? Let's go ahead and move on to the next example. Now we're going to be seeing something called non-negative restrictions. What non-negative restrictions do? So non-negative restrictions, well, the good news is they always look the same and they always perform the same role every time. Non-negative restrictions means that we generally use these a lot in word problems. Whenever we have objects that x and y are referring to that can't necessarily be represented by a negative number. Maybe distance, or time, or weight, things like this. All of these are values that do not take on negative values inherently. But what we do with non-negative restrictions every time, as soon as you see these in a problem, that means you always need to put a solid line on the x-axis and the y-axis. Always put solid line on x, y-axes. And the way you do that using the graphing tool in my math lab, as long as you plot any 2 points, on the x-axis, it will draw a horizontal line for you. It doesn't matter where you plot the points. You just need a horizontal line on the x-axis. That's one of them. And then you need a vertical line on the y-axis. Again, it doesn't matter where you plot the 2 points. These would be the non-negative restrictions applied. You do this anytime you see the phrase non-negative restriction, you should put solid lines on the x and the y axes on your graph. If you don't put them, your problem's going to be counted wrong. And we'll see this throughout this section. This comes up quite a bit. So that takes care of 2 of these inequalities. Now there's also the non-trivial one that they gave us over here on the left. And they also want us to graph this inequality, which we know how to do because we've been talking about it for the last few examples. And since that was last week, hopefully this process will jog your memory. So the first step we did was we had to graph the underlying equality. And since it's not easy to put this into mx plus b form, you can if you want, but when it's in this form here, I generally use x and y intercepts. So remember, with this, the x-intercept, we set y equal to 0. And you solve for x. Then we get that x, looks like x is 100, which corresponds to the ordered pair 100, 0. And that gives us 1 point on the graph. Now it looks like on the x-axis, the increments go by 50. So it looks like that would be right here, or 100. We can do the same thing for the y-intercept to find a second point, so we can actually construct the line. For the y-intercept, remember that's setting x equal to 0. And then you solve for y. It's at -60. Oops, forgot the y. Y, there we go. We get -60. So the y-intercept, we get -60, which gives us another point that we can plot. -60, these go by increments of 10 on the y-axis. And then from here, since we have 2 points, you can go ahead and, well, on my MATLAB, it will automatically draw the line for you. In our case, I just use the workbook, try and loosely draw this line. Good enough. Okay, so from here, we have the 2 non-negative restrictions. Those are the solid lines on the axes, which you have to do by default. And I made a mistake here, didn't I? What mistake did I make? What mistake did I make here?
It should be dotted.
It should be dotted. I forget that every time. So maybe I should switch 1 and 2 next time I teach this class. I should do solid or dotted first. So the second step, if you look back in your notes, we always did the second step as solid or dotted. But this one's going to be dotted. Remember, this is based off of what inequality symbol do we have? Does our inequality symbol have an equal to part? Well, it doesn't look like it. It looks like we have strictly greater than. Strictly greater than. There's no equal to part, which means you have to use dotted. So if you already drew this line, you can actually just erase this. It'll serve the same purpose. So it should be dotted. Remember, that doesn't matter in this section. It should be a dotted line. So again, this is no equal to and the inequality. If we did have an equal to, then we would use a solid line. Let's move on to 3, which is shading. Because with inequalities, just graphing the lines is not enough. For inequalities, you also have to shade a particular region. Now, there's 3 lines going on here. So there's a little bit more restriction than what we're used to. And when you see the words non-negative restriction, not only do you have to draw solid lines on the x and y axes, but you also This also tells you that you can only shade in the top right region of the graph. Only in the top right region of the graph. So the top right region, everything over here, everything over here. This is also known as the first quadrant. Basically, this is telling you you can't shade in any of the negative regions. You have to shade in the non-negative regions. And the positive region's the top right one. So now this puts us in a position of, well, now we know we're not looking at any other region but that top right region. But there's a black line that cuts through the region. It splits up the top right into two sections. We have a section here on this side and a section here on this side. And our goal is to figure out which side do we shade. Do we shade what I called I here, or 1, of course, Roman numerals, or 2 over here? That's the question here. We don't shade any other part. We don't even consider any other region because the non-negative restriction said only look at the top right. Now, how we do this is the same way we did before. I like to pick the test point 0, 0. So 0, 0, just to remind everybody, is right here in the center. So if 0, 0 satisfies the inequality, we're going to shade the region closest to 0, 0. If 0, 0 does not satisfy the inequality, we shade the region away from the origin. That's what we're ultimately trying to determine here. So the inequality that we started off with was 15x minus 25y is greater than 1500. We plug in zeros for x and y. This is what we did last time. And so we get that 0 is greater than 1500. Obviously, this is a false statement. Shade, really shade away from 0, 0. So 0, 0 is right here in the center. We want to shade the region that's not touching that point, which ultimately comes down to this region over here. That's the region not touching the point 0, 0. And again, this is where you, if you are interacting with the graphing tool, this is where you would pick the paint buckets and you would click in that region. And notice the region doesn't go any further. It does not expand past any of the line segments because you are stuck in the first quadrant. You are stuck in the top right region. And that would be the final answer here. This is what we call a system of linear inequalities. System being more than one inequality at play here. So we basically have to shade in accordance to all the lines. Does anyone have any questions before we look at a fairly similar problem? If not, let's move on to example 9. So as you can see, this is a word problem. So all of the wording aside, it takes 3 minutes to cut the foam for a regular mattress, 6 minutes for a king mattress. So they're telling us 3 corresponds to regular, 6 corresponds to king. It does go on to say X corresponds to regular, Y corresponds to king. So somehow 3 is going to correspond to an X and 6 is going to correspond to a Y. 3x plus 6y. Additionally, well, this is not complete. What sort of equation or inequality do we have? If the cutting department has 30 hours available each day, So as you would imagine in this section, we should have nothing but inequalities. So if anything, the inequality symbol that we use, and this one's probably the more difficult of the word problems here, they have at the most 30 hours available for, well, labor hours available. So what we have here is that the max number of labor hours, as they call it, is 30. So I'm using less than or equal to, because for this 3x plus 6y, it cannot exceed the 30 hours. But I am not going to put 30 next. Why is that? It's in minutes. That was a sneaky detail that definitely tripped me up the first time I saw it. This is in hours, but they gave us 3 and 6 in minutes. Minutes and what's the other one? Minutes. So we need to convert the 30 hours to minutes. To convert from minutes to hours, if there's 30 hours, but you multiply that by 60. I think that's 1800. So that is our inequality. And I'm pretty sure presented to you, it's going to be multiple choice. So if you're wondering where 1800 comes from, even though 1800 is not even in the paragraph at all, that's where it's coming from. I believe the other ones are a lot less tricky in that regard. This one's the tricky one, I believe. So from here, we also say, so we're not done, but what follows is not too insane. Non-negative restrictions. They also throw in the phrase non-negative restrictions. And anytime I see that, I instantly have to consider x is greater than or equal to 0, y is greater than or equal to 0, just like above. It's like this above example that we did. So those last two inequalities I just put, that's due to non-negative restrictions. And anytime you have non-negative restrictions, you need to put a line on the x-axis and a line on the y-axis, a solid line. So here's a line on the x-axis. Again, to plot a line in my math lab, you need to plot 2 points. It doesn't matter where the 2 points are, you just need a horizontal line on that axis. Same with the y-axis. And it doesn't matter where you put the 2 lines at. So those take care of the non-negative restrictions. Now we move on to the inequality that we found. The 3x plus 6y is less than or equal to 1800. We'll start off with the underlying equation. And again, because it's written in this form, you can go and write this as a, well, as slope-intercept. But when it's in this form, I like to find the x and the y-intercept. We'll start off with the x-intercept. So this is 3x is equal to 1800. Because setting y equal to 0 makes that whole term go away. And so x is 600. And that gives us a point right here. I'll put this one in blue. X is 600. Y-intercept, we set x equal to 0. So that means the x term goes away. 6y is equal to 1800. Y is 300. So if y is 300, that's about right here. Because on the y-axis, it seems to go by increments of 100. Well, same with the x. And now that we have the 2 points here, of course, in my math lab, it will just generate this for you. Here we go. Now, with the non-negative restrictions in place, oh, and also, well, luckily the line is solid. The line is solid because there's an equal to part in our inequality. There's an equal to part in the inequality. So the line should be solid, so I don't have to modify anything here. Now we need to worry about shading. So one question we need to ask is, well, what are our options for shading? Now the non-negative restrictions tell us you have to only focus on the top right. The blue line that we drew in addition to that splits that whole top right region into two regions. This region down here and this region up here. Notice this only stays in the top right region, which is really bounded by that right angle. So we need to figure out which one of these regions do we shade. Do we shade 1 down here, or do we shade 2? Well, we could pick a test point. Of course, 0, 0. I'll draw 0, 0 right there in red, right in the center. So if 0, 0 satisfies the inequality, we shade the region that touches that point. We test 0, 0 and it fails the inequality, we shade away from that point. We shade the other region. So we test 0, 0. The inequality, I'll just remind everybody what it is. You plug in 0 for x, 0 for y, and everything zeroes out. And we get a true statement. Shade next to 0, 0. So we want to shade this region down here. We want to shade that region that is adjacent to the origin. And again, this is where you would put the paint buckets at. And that would be your final answer here. Again, the shaded region does not extend past the non-negative restrictions. You are confined to the top right of this graph. Does anyone have any questions before we look at the next problem? Let's go ahead and move on to example 10, which gives us a system of, well, non-trivial inequalities. There's no more non-negative restrictions here. So with this, we need to graph both of these lines, shade, and all of that stuff. So what I like to do, this might be good if you have multicolored pens or something like that, but if not, I like to give these names, because giving these names will be important for shading later on. I'll do all the stuff for L1 over here. For the first line, I'll do all the stuff for the second line over here. Which means individually, we will need to plot the lines and then figure out which region to shade. I'll start off with graphing x minus 4y is equal to -8 as the underlying equality. Means we need to find the x and the y intercepts. The x-intercept, y is 0. So x is -8. Gives us a point right here. The y-intercept, x is 0. With that, the x term goes away, so we're left with -4y is equal to -8. In other words, y is +2. We ask ourselves also, do we get a solid or a dotted line? Here we get a solid line because the corresponding inequality has an equal to part. So we use a solid line. Now I'm going to leave it at this. I'm going to shade whenever I have both lines plotted. This will make more sense here momentarily. So let's start off now with the other line. The underlying equality is 3x plus y is equal to 6. And let's go ahead and find the x and the y-intercepts. Set y equal to 0, 3x is equal to 6, so x is equal to 2. Y-intercept, we set x equal to 0. And so this one works out nicely, y is 6. And then we ask ourselves, do we get a solid line or a dotted line? The underlying, well, the inequality here has an equal to part. So this will be a solid line. We'll go ahead and draw that one in as well. So now we have our two lines. So if you don't have multicolored, pencils and all that stuff, it's just good to put labels next to each line to remind yourself that that's the first line and that's the second line. This will be helpful here for the shading purpose. You want to know which line is which. Because when you start to shade, well, really our whole graph is split up into 4 regions. Here's a region, here's a region, here's a region, here's a region. And we need to figure out which one of those regions do we end up shading. Now, this comes down to doing the shading process for both of these lines. So we'll start off with red. We'll test 0, 0 for the red line. So remember, 0, 0, we'll do this in purple, is down here. If 0, 0 satisfies the inequality, we shade below the red line, near the point. If 0, 0 fails, we shade above the red line, away from the point. So we have x minus 4y is greater than or equal to -8. If we plug in 0 for x and y, you get that 0 is greater than or equal to -8, which is true. So we shade near 0, 0. So that means for the red line alone, this completely ignores, for the first line, we completely ignore the second line and we will be shading underneath the first line. which means we are not shading 1 or 2 up here. We do not shade above the line. So now we're only down to 2 regions here, because we are shading near the origin, the purple dot. And all of this, of course, ignores the second line here, because now we have to test the second line. Now, for the second line, or on here, the blue line, now we're trying to determine, do we shade to the left of the blue line, which means we shade near the point, or do we shade away? That's what we get to find out. So the inequality is 3x plus y is less than or equal to 6. If we plug in 0 for x and 0 for y, get that 0 is less than or equal to 6, which is true. So for the blue line, you shade nearest the point. So that gets rid of region 4 here, because that's away from the point. So we are left with this region 3 here, which would be the correct region. Or in both cases, for both lines, we shade nearest the point. So that's the region we shade. Or this is where you would put the paint bucket tool at. And it would shade just that region after you plot both lines. And that would be the solution for the system. Does anybody have any questions before we look at the next problem? If not, let's move on to example 11. Now, example 11, the good news is they drew the lines for us. And we need to figure out, very similar to before, which one of these regions do we shade? Now, notice the regions are sort of collected, they're sort of bounded because they also have non-negative restrictions here, which means they already put lines on the x and the y axis. And in fact, they already zoomed in the graph to only look at the top right region. So that's what we're looking at right now, with the axes being the more shaded in lines here. So the first thing we have to do, if the first line, we call it L1 or something, and the second one is L2, we need to figure out which line corresponds to which. Now, one indication of this, I see a 15, and there's a 15 down here. So I would assume that, well, I guess to match my coloring scheme, there's a 15 here and a 15 here, then L1 would be the red line, or the first line, which by process of elimination, this would be the second one. Another indication, there's a 12, there's a 12. And if you find the y-intercept, you would be able to verify that. So they already drew the lines for us. And all you would have to do is say, okay, well, this first one is L1 and this one's L2. Just to give yourself some sort of notion as to which one is which. And this is important because we need to shade from here. We need to figure out which region to shade. Now we'll start off with L1 here. X plus 3y is less than or equal to 15. And for shading, we don't have to do any of the other steps because they graphed everything for us. We're going to, again, test 0, 0. Now the first line, so I have it labeled right here. We're checking to see, do we shade on the same side as the origin, which I just dotted in there. It's on the bottom left now. Do we shade near the point, which would be regions 3 and 4, or away from the point, which would be regions 1 and 2? Remember, this is all in relation to the first line. The second line, we ignore for now. So now we can plug in 0 for x and y. And we get that 0 is less than or equal to 15, which is true. So what this tells us, shade under L1 near the point 0, 0. So that means we would shade either region 3 or 4, because those are both under the red line, or the first line, which means 1 and 2 are out. 1 and 2 are out. So let's do the other line to figure out which one of 3 or 4 is the correct region to shade. 2x plus y is less than or equal to 12. So we test 0, 0. So this would be 2 times 0 plus 0 is less than or equal to 12. 0 is less than or equal to 12, which we get a true statement. So here, for the second line, the blue line, as I have illustrated here, shade under L2 near the point 0, 0. So the two regions that are, I guess, technically under or to the left of the blue line, that would be 2 and 3. But we already marked out 2, so it's got to be 3. So it has to be 3. That means 4 would be out because 4 is not under the blue line. This means that region 3 would be the correct region here. Region 3. But we're not done. They ask for one more thing. They also want us to identify the unknown corner point of the solution region. Now, what's a corner point? So our region was region 3, which is highlighted here. This region has 4 vertices or 4 points that pretty much comprise its geometry. This point right here, the origin, this point up here, this point of intersection, and this point down here. These 4 vertices ultimately make up this region, or these are all the regions in which 2 or more lines intersect. Now, 3 of these points are already known. We know the origin, we know the y-intercept, we know the x-intercept. So the question is, this is the unknown corner point. But the good news is we can just look at the graph and tell what it is. Let's see, I think the x-axis goes by increments of 2. So this is actually 4. And then if this is 2, 4 here, I think that's 4, 4. So I believe that's 4, 4. And so that would be the unknown corner point. And you could tell that by just looking at the graph. That would be solving a system by graphing, as we talked about in the very first section of this unit. Does anyone have any questions before we look at the next example? Okay. Let's move on to example 12. So we want to solve this system graphically. They also want us to determine whether the solution region is bounded or unbounded, and then find the coordinates of each corner point. Okay, so we have a few instructions here. The first instruction, though, shouldn't be any different than what we've done before. They want us to graph this solution. It seems like a lot going on here. Two of these are pretty easy though. These are the non-negative restrictions. And with those, that means you always put a line on the y-axis and a line on the x-axis. So I'll go ahead and do that first. That already takes care of those two. Okay, so that's two of these four that we already knocked out. For the other two, this is when we need to label them in some way. This will help with shading later on. And figure out what their lines look like. So I'll do both of these off to the side. Now from here, it's the same steps as before. You graph the underlying equation. I'll start to go a little bit more quickly, or move a little bit more quickly through these intercepts. So here, x would end up being 4. You set y equal to 0, 2x is equal to 8. So x is 4. The y-intercept, y is 8. So that gives us 2 points to plot. 4 and 8. Now we asked, before I draw the line, is the line solid or dotted? This is going to be solid. Solid because the inequality symbol has an equal to part. Simple as that. So we can go ahead and draw a solid line. Okay. And I'll hold off on the shading until we plot the other line. X plus y is equal to 6 is the underlying equality. Looks like the x and the y-intercept are both going to be 6. Six, 6. And it looks like this one's also going to be solid. Again, it's solid because we have an equal to part in our corresponding inequality. So here's our 2 lines along with the non-negative restrictions. So from here, we need to figure out which region to shade. The non-negative restrictions tell us we're stuck with the top right region. And the 2 additional lines that we drew tell us that we have now 4 regions to look at. We have this region here, this small region right here, this region out here, and this region down here. Notice how we're staying in the top right quadrant, the first quadrant here. And with that, we have 4 regions that we need to go through. This is very similar, actually, to the above problem. It's very similar, except here they just didn't zoom in on the top right quadrant of the graph. So here, we need to test, and again, this is, if you don't have colors, this is a good way to say the first line you drew is L1 and the second line you drew is L2. That's definitely important as you try to figure out what line to shade to which side of. So we'll go ahead and test 0, 0. So this is 2x plus y is less than or equal to 8. If you plug in zeros for x and y, you'll get that 0 is less than or equal to 8, which is true. That's a true statement. So for the first line, we need to shade under L1 near 0, 0. So for the red line, or for the first line, we need to shade underneath it. That instantly gets rid of regions 3, because that's not under the red line, that's above. And region 4, same idea. So now we're down to regions 1 and 2. 2 is that very tiny region. It might be a little difficult to see. So we move on to the second line, because regions 1 and 2 are separated by the second line, the blue line. So we need to figure out which one of these we select. So let's test 0, 0. Here we have x plus y is less than or equal to 6. Everything zeroes out on the left. We get that 0 is less than or equal to 6, which is true. So we shade under L2 near 0, 0. So we shade under the blue line, which means we get rid of that second region we had. And we're left with region 1, because that is the region that is closest to 0, 0 for in both shading situations. So that's the region we shade down here. Or in other words, this is where you would put that paint bucket thing. And it would shade for you. And then for part B, because part B is pretty simple, part B is asking, is this shaded region bounded or unbounded? So is this region we just shaded, is that a bounded region or an unbounded region? So bounded means, is your region surrounded on all sides by line segments? Well, our shaded region has a line segment here, line segment here, line segment up here, and another one up here. This might also be intuitive as well. This is a bounded region. This region is completely bounded on all sides by line segments. Now, if we were to have shaded out here, this would be unbounded. There wouldn't be line segments restricting it at the top. But we have a bounded region, though. And this idea of boundedness does come up a little bit later. And then finally, it wants us to determine the coordinates of each corner point of our bounded region. So our bounded region has 4 corner points. The origin, in fact, let me do this in purple so it contrasts nicely. The origin, this intercept up here, this unknown corner point, and this x-intercept down here. These are the 4 corner points. Again, a corner point, you might be able to intuitively see what they are, but also it's characterized by when 2 lines intersect. And they want us to determine the coordinates of all of these. The first one is 0, 0. That one should be obvious. And for part C, so that's ultimately what we're answering here. What are the coordinates of each corner point? The one up here, 0, 6, because that's a y-intercept. That one's pretty easy to find. This one over here, is 4 comma 0. Then what about this corner point right here? So you might be able to use the graph and determine that this is the point. It looks like it's 2 comma 4 by using the grid lines and trying to trace and see where it might intersect at. So the question is, how absolute are you on this? What about if we have a problem where the intersection is not as easy to find? Well, this is the intersection between L1 and L2. How do we figure out where two lines cross? We can use matrices. So matrices come back. Now here you might be able to say it's 2, 4, because normally my math lab gives you pretty nice graphs, but not always. So to figure out how these two lines intersect or where they intersect, this is where we did that augmented matrix stuff, where we took the coefficients, we constructed a matrix out of them. And just to demonstrate this, so remember what we did in that section. Go to the matrix menu, edit in the matrix. This would be a 2 by 3. From here, you'd have to apply the RREF command. So this is what we talked about in class for the augmented matrix section. We get exactly this, which tells us that the point 2 comma 4 is the point of intersection. This is one application of this. So that's the last corner point. It's 2 comma 4. Again, for this problem, it might give you a very nice graph for which you could just tell what the corner point is, or you might have to use a matrix. So for any of you who might still be writing, give you a few seconds on that. Does anyone have any questions about any of this? I mean, the good news is it's fairly sequential. It's just very tedious. Do you have a question?
Okay, so for the restrictions, if the like greater than or equal to sign was flipped, would that like change it, or does it matter?
As far as the two bottom ones?
Yeah.
So the good news is for non-negative restrictions, the signs will always stay as greater than or equal to. Now, if these inequality symbols changed, where we shade is going to change. But the bottom, for the non-negative restrictions, those are just default. Those will never change. They will always be x is greater than or equal to 0, y is greater than or equal to 0. Okay. Well, if there's no other questions, let's move on to the next example. And as you can see, this is a word problem. Okay, so admittedly, I have a horrible time trying to pronounce that word, so I'm not pronouncing it. I'm not attempting to. You can make fun of me all you want. I'm just going to skip that word. There's two types of skis. One of the skis is associated with 10 hours for fabricating, and 1 hour for finishing. There's another ski, which I'll underline this information in red. 6 hours for fabricating, 1 hour for finishing. So we can see a little bit of overlapping information here, something about fabrication and finishing. Then they also tell us, I guess I'll do this in a different color, the maximum number of hours for fabricating and finishing are 150 and 20. So these are the three real subsets of information here. And they do go on to tell us X represents these type of skis, Y represents these type of skis. So the question is, how do we write inequalities based off of all this information? Well, if X represents trick skis, then we need to find the numbers that correspond to that. So for this ski, we have, so for X being the number of trick skis, it seems like we have 10X and plus, I did this differently in a different class. Why am I drawing a blank? So I thought it would be 10 and, was it 6? Okay, that should be 10X plus 6Y. Let me write it out and I'll convince myself why that is. Maximum, I'm just drawing a blank, I don't know why. I just taught this. Maximum number for fabricating, so the fabrication number should be together. So that'd be 10 and 6. So this is right. Oh, okay. Fabricating time, that's why. All right, so, all right, that makes sense. So for fabricating time, it's saying bring all the numbers corresponding to fabricating time together. Because that's what it says for part A, fabricating time. Yeah, sorry about that. So 10 hours for fabricating, that's why I put 10 here. And since that corresponds to the first ski, that's why I have an X. The next time I see the word fabricating, 6 hours for fabricating. That's why I have the 6 for that one. And then it says the maximum number. So maximum meaning I need to use a less than or equal to sign because 10X plus 6Y cannot exceed the 150. That's why I have the less than or equal to symbol. And it says the maximum for fabricating is 150. So I'm putting all the fabricating numbers together. And I'm going to do the same exact thing for finishing. Now the first one I see, 1, so that'd be 1X. And then I go on to see 1 for the next time I see the word finishing. Again, it says maximum, so I'm using the same inequality symbol. And it goes on to say that the max is 20. And since 1X and 1Y don't really mean anything in terms of the ones, I'm just going to put X plus Y. Just going to put X plus Y. Those ones don't really do anything. So those are the two inequalities here. So they wanted us to set up the system, and then they want us to graph it. Now, I think it's a good idea to, off to the side, state the system that we really have here. The system that we have, so obviously we just found 10X plus 6Y is less than or equal to 150. We have X plus Y is less than or equal to 20. But we also have two other inequalities. Now they don't state it here, but we need non-negative restrictions. So you might think, well, why do we need that? It doesn't say anything about them, which is fair until you realize X and Y represents number of skis. And with the number of skis, well, the number of skis cannot be a negative number. It has to be a positive number. So the non-negative restrictions, which always have this form, must also be incorporated. And so that is the system that we are going to be graphing here. So this is going to be very similar to the previous problem we did, where they gave us a similar system. So it's the same problem, it's just we had to set up the inequality first. And so with this, I'm again going to first graph the non-negative restrictions. The non-negative restrictions means you always put a solid line on your X and Y axes. There's your Y axis. And there is your X axis. So that's step one. So that takes care of those. Now we need to illustrate the two non-trivial lines. Again, I'll call one of them L1. I'll call one of them L2. We'll do both of these off to the side. L2 I'll put over here. So for the first one, we need to graph the underlying equality, which means we need to find the X and the Y intercepts. So we set Y equal to 0. We end up getting that X is, I believe, 15. And the y-intercept, we get that y is equal to 25. 25. So there's 15, and there's 25. Again, the x-intercept is found by setting y equal to 0. I'll let you figure out the little bit of algebra there. Y-intercept setting x equal to 0. Same idea, I'll let you figure out the algebra there. You should get 15 and 25 respectively. Then we ask ourselves, do we get a solid or a dotted line? This one's normally the easiest one to find. We have a solid line, because our inequality that we had has an equal to part. So I can go ahead right fast and connect those two dots. And I'll leave the shading to the final step. Okay, let's start off with the underlying equation. And it looks like the x-intercept and the y-intercept are both going to be 20. And before we connect the two dots together, we need to figure out how to do so. We have a solid or dotted line. Looks like we have solid again, because yet again we have an equal to part. Okay. And then we just need to figure out which region to shade, because we have four regions here. So we have four regions, and we need to figure out which one of these do we actually shade, which means we need to test 0, 0. So we test the origin. Remember, the origin is down here. Again, if you don't have colors, then this is good to say that L1 is the first line you drew and L2 is the second line that you drew to help distinguish which line is which. So we're testing the first line. This was 10x plus 6y is less than or equal to 150. You plug in zeros for x and y. You'll get that 0 is less than 150, which is a true statement. So you shade underneath the first line, or in this case, the red line. Which means we can get rid of the regions that are not under the red line. That's 3 and 4 here, because they're both above the red line. So we're left with 1 and 2 again. This should seem kind of familiar. It seems like we did a problem fairly similar to this, which we did. For the second line, or the blue line here, we need to test, again, test 0, 0, which will tell us if we shade region 1, which is below the second line, or above. So x plus y is less than or equal to 20. We plug in 0 for x and y. Get that 0 is less than or equal to 20, which is true. So we shade under L2. Which means the second region here is not under L2, so we get rid of it. And we're left with region 1, which is the region we want to shade. Or this is where you would put that paint tool at. Does anyone have any questions about this one? Of the section, example 14 is no different. The only difference is, well, we're going to have 3 inequalities for this one. All the previous ones, we've had 2 inequalities. So the first thing it wants us to do is write an inequality for phosphoric acid. Now, when I read this paragraph, when I do word problems, I just look for the numbers as they pertain to the whatever noun we want. So I see phosphoric acid. See 24 for phosphoric acid. And designate that with an X. We keep reading and see what the next reference to phosphoric acid is. All right, I see phosphoric acid right here, and it says 12 pounds of that. And then I'll do plus 12. I guess I'll call that one Y because I already used X. All right, let me keep reading. Minimum monthly requirement. That gives me an idea about an inequality symbol because, of course, we need an inequality. 480 for phosphoric acid. And so by saying the minimum monthly requirement, that means we need a greater than or equal to symbol, because what it's saying is that our expression here, 24x plus 12y, at the minimum can be 480, but it could be larger than that. So we need to use greater than or equal to, because that establishes that 480 would be the minimum. And so this process is going to be continued for, say, nitrogen here. I see 30 pounds of nitrogen, so 30x. The next reference for nitrogen, 30 for nitrogen again, just put 30y. The minimum monthly requirement, so that's still the same inequality symbol. And the next reference to nitrogen is 900. 900 pounds of nitrogen. Finally, we can move on to, I'm guessing it's pronounced potash. I'm not too sure. We have 6 pounds of it though. 6x. Keep reading to see 24 pounds for the next part. Minimum monthly requirement, same inequality symbol, and it says the minimum is 240. So basically, I took all the numbers, associated them with the nouns or the subject of each part, and then I constructed an inequality based off of minimum monthly requirements. So we have 3 inequalities from this in total. Now, what I like to do, and I did this in the previous examples, I like to write all of the inequalities off to the side. And so by doing this, it gives me an idea of what system we are working with. So 3 of these are already written, so I'm just rewriting them. But in addition to these, there's actually 2 more inequalities at play here. And the 2 other inequalities are the non-negative restrictions. Now, one implication that we have non-negative restrictions, you can basically just look at the graph. The graph is zoomed in on the top right. We're not looking at the whole graph. It's zoomed in one particular region. Another aspect of this is that x and y, if we just scroll up, x and y seem to refer to, I think I wrote yards here. That shouldn't say yards, that should say pounds. Or should that be yards? Oh, it should be yards, okay. It should be yards. In any case, yard is a distance, and distance is normally positive. So we are dealing with positive values, or technically non-negative, because yards could be 0 as well, in theory. So we are, even though it does not say non-negative restrictions, we are asserting that here, that is a necessary condition, and this is normally common with word problems. Because with word problems, we normally deal with objects that are non-negative, either 0 or positive. Which, as soon as you see non-negative restrictions, as we did before, we put a solid line on the x and the y axes. And soon enough, I'm going to ask if I can borrow someone's workbook. Actually, no, I don't need someone's workbook. I can use this now. You draw straight lines. Okay, never mind. Use that. All right, so let's go ahead and start drawing the non-trivial lines. Now we have 3 lines. We haven't dealt with 3 lines before. So I normally like to use a labeling scheme because 3 lines going on at once, you need to know which one's which. So on my notes, I'm going to use different colors. If you don't have different colors, that's perfectly fine. I'll show you how you can, well, ultimately you could just put these labels next to the line that you draw. But from here, let's go ahead and start off with the first line. 24x plus 12y is greater than or equal to 480. So we'll start with that one, and we'll do what we did before, find the x-intercept and the y-intercept. Now, I'll do one example of the x-intercept, and for future problems, I'm going to skip through this step. This is whenever you set y equal to 0. And you do this for the underlying equation. So this is what we talked about before. We're doing it again here. 24x is equal to 480, and we can quickly solve for x. X seems to be 20, which gives us 1 point on the graph for the first line. Do the same thing for the y-intercept. Where we set x equal to 0. It's a very similar process. So get 12y is equal to 480. And we can quickly solve for y. Y seems to be 40. Y is 40. We ask ourselves, is the line that we construct, is that going to be a solid line or a dotted line? The next part. So that was 1, and this one is 2. So we ask ourselves, is the line solid or dotted? And the answer is the line's going to be a solid line because the inequality that we are analyzing here has an equal to part. That's the only condition. The inequality symbol that we were looking at has an equal to part. Because of that, solid immediately. And now we can go ahead and draw a solid line connecting these two dots. Just like that. So again, if you don't, I would imagine a lot of you don't have different colored utensils, that's fine. Make sure you put an L1 next to that line. You need to label that line in some way, and this is the only way I can think of doing it as simplistically as possible. So that labeling will be important. And we're not going to worry about shading quite yet because we have more lines we need to graph here. So we're going to move on to the second line, which is 30x plus 30y is greater than or equal to 900, and do the same exact process. And so the first step, we need to find the intercepts. So when finding the intercepts, again, I'm just going to skip through this a little bit. X-intercept, you will find that it is 30, and the y-intercept, you will also find that it is 30. By using the process on the left side of the screen here, which gives us 2 points on the graph that we can plot. Now, we ask ourselves, is the line connecting them solid or dotted? And because the inequality symbol, yet again, has an equal to sign, it's going to be solid. So we can draw a solid line connecting the two. Then we'll do the third inequality down here. So let's see, that one was L2. This one will be L3. That is the 6x plus 24y is greater than or equal to 240. And so, again, we need to figure out the x and the y intercepts. The x-intercept seems to be 40. Again, whenever you set y equal to 0 and divide both sides by 6, you will get 40. Gives us 1 point. And then the y-intercept, seems like you will get y as 10. After you set x equal to 0 and you divide both sides by 24. Then you get 10. Again, we ask ourselves, is the line solid or dotted? Well, the underlying inequality has an equal to part in its inequality symbol, so it's solid. And so yet again, we draw a solid line connecting these 2 points. So something like that. Now that we have all the lines constructed, now we need to figure out what's the shaded region. So to determine the shaded region, we need to test every line and And again, to be consistent with the labeling, the second line we drew, it'd be good for you to put an L2 next to it or something to remind you that's the second line, and then this one L3. Mind you that this line is the third line. So from here, we need to go ahead and test each line because there's technically, there's quite a few regions going on here. There's 1, 2, 3, 4, 5, 6, 7 regions here. There's 7 regions here. We only need 1 region. We need to figure out which region we end up shading. We're putting the paint bucket tool at. So let's start with the first line. And we always test 0, 0. And ultimately what this is telling us is do we shade under that corresponding line or above that corresponding line? So what we're doing, and I'll write it out here explicitly, we're plugging in 0 for X and 0 for Y into the corresponding inequality that we are testing. And usually what always happens is that the left side will zero out. When you're multiplying and adding by zeros, this is typical. And we ask ourselves, do we get a true statement or a false statement? Obviously get a false statement because of course 0 is not greater than 480. And whenever you get a false statement, what this means is you shade above the line. And this line that we're testing happens to be L1. So we are shading above, as I illustrated here, the red line. Or in other words, we're shading above L1, which means we're not shading. So really, this region, this region, this region, and this tiny region down here are still left into consideration because those are all above the first line, which means we get rid of all these other ones because of course they're not above the red line. So we can get rid of them and now turn our attention to these 4 remaining ones. Let's do the same thing for the second line, the blue line, where we will again test 0, 0. Again, we are plugging in 0 for X, 0 for Y. And we get a false statement, which means we will shade above the blue line or the second line. Shade above the second line. Now what that does is that keeps this region here and this tiny region down here and gets rid of those two because those two are under the second line. So we can get rid of this one, get rid of this one, and we're left with 2 regions. And yes, there is a very tiny region right down there. So there's 2 regions left. We need to narrow it down one more time by testing the final line. So for the final line, we test 0, 0 yet again. We plug in 0 for X, 0 for Y. We get that 0 is greater than or equal to 240, which is again false, which tells us we shade above the third line or the purple line here. So that gets rid of this tiny region all the way down here. And leaves us with this outer region up here. And that will be the region that we ultimately shade. So again, if you put your paint bucket tool, again, this is a good chance for you all to make fun of my artistic skills. So that paint bucket looking thing, you would put that in this region and it will shade all of this for you. And that shaded region is your solution. You don't have a shaded region while graphing inequalities, then you haven't completed the problem. That's the final answer.